Howdy, and welcome to review of schematic capture printed circuit board design. So we're going to look at a project, the project that we actually talked about in the introduction of using Altium. This is obviously a very simple uh, project, probably a little bit similar to some of the projects that you might be actually doing in this class. So it just completely depends on what exactly you're doing. Um, Basically, we have a simple microcontroller that is going to be reading a thermocouple, just a temperature sensor, controls a relay on and off, have a simple user interface. In case we have 4 push buttons, display the temperature on a 7-segment LED display, have a few other LEDs for enunciation, and take in 8 to 30 volts DC, nominally 24 volts. So a fairly straightforward project. And so what I'm going to do is I'm going to go over the schematic and go over the circuit boards for both the LED board, the microcontroller board interface, and just kind of high level give you an idea and a tour of some of the things around Altium, hierarchical designs, and things like that. So overall, that is the goal of this presentation here. So let's go ahead and get started. So this here is Altium. Like I said, we've kind of introduced this already by creating symbols and footprints. So we're going to assume in this video that all the symbols and all the footprints have been created, whether you get those online from or through Altium through their manufacturer part number search system, or whether you created them yourself. Regardless, everything has been created. So all footprints and all symbols. So now we're actually looking at the design. So we're going to be looking at completed schematics here, but I'll show you the kind of the process for once you kind of put the symbols on the page, what's involved. So here is our first page. This is the hierarchical design for the main controller. And this here is a 5-page document. There is one main page and then 4, if you will, hierarchical or sub pages that go under it. So the nice thing about hierarchical designs is that it basically shows the structure of your design and breaks it down into a kind of a block diagram elements and kind of encapsulates a system into an object, in this case, what's known as a device sheet. That's what these are here, so that we can represent an entire schematic as just a block. Um, Obviously, this is kind of a mixed design where actually on the hierarchical main page, I also have parts. So let's start from kind of the power in, and we're just going to wrap around the entire board here and going over through everything. So this system has basically a connector. So every system has connectors, input and output connectors. So don't just think about, well, I've got this design. Now, how do I connect power to the board? You connect power to the board through a connector. You actually buy these. So this, and I will show this to you in a little bit in the 3D view of the board, but this is a terminal block that has a plug, so you can actually hook wires in here to, if you will, to the left-hand side of this plug. You hook up in 9 wires. You push the plug into the receptacle, which is the terminal block, and it would plug into the board. This right here is basically removes from the terminal block, and so an electrician would wire their wiring to this, and that would then plug into the terminal block, and the terminal block is actually what is on the board. This actually is a mechanical part, as it's called. In fact, you can see in here it's listed as a type mechanical. So this is included in the bill of materials when a bill of materials is produced out of Altium, but it's not actually a circuit board component. Most of the things you're going to do are going to be what we call standard parts, which means it actually has a footprint. So this does not have an associated footprint. See, it says footprint is missing here on the right. But you can see in part choices, it shows, because Altium's are good if it's got all the information of the part itself, which all of the, in my case, all the manufacturer part information, it will dig it up online and tell me that this part here is from Phoenix Contact. They're expensive. They're $18 a piece. There's 145 in stock at whatever company they're pulling this from right now. Anyway, so we got this terminal block. And so on pin 1 is our power, our 8 to 30 volts DC. And we're going to go into this first block here, which is a DC to DC converter. So these are known as device sheets. You can right click and go place device sheet. So we do a sheet entry. Let's see, actually it's placed. I usually just cut and paste these things, to be honest. So place, let's see, a sheet symbol. And this is how you can assign it. So you assign a designator, my sheet name, and you assign it a file. So the file is part of your project. So you go ahead and you would have designed all the subsheets first before you design this. And so we could say assign a microcontroller. And as soon as you do that, you get a sheet. And so after you do that, if you want to have all these parts here, so we need to call this my sheet name MCU. And we're just going to make it a real quick clone just to show you the process for creating a device sheet. And I come here to sheet symbol actions, and I synchronize the sheet entries and ports. So this, and I'll show you here in a minute, there's ports in every one of these. In fact, let's go ahead and instead of the MCU, because we're going to be showing you the power first, we'll just do power again, rename it, and we'll choose the power system, which is a DC to DC converter. And we'll come up here and we'll do synchronize, and it comes up and it says there is a power port that is on the sheet, and I'll show you that in a second, and it will drop here on the page. And as you can see, other than adjusting some graphical elements, basically I have these a little bit of a teal color of a larger border, things like that, that all of this can be adjusted here, line style, different colors. I can make it red if I wanted to. So you can change your sheet to be whatever you want. And then now this is pretty much, these two are for the most part identical. So I'm going to go ahead and delete that, and we'll go back here. So that is what these are. These are device sheets. So when it compiles and it sees a device sheet, Altium, if you see on the left-hand side, will automatically make a hierarchical tree because it sees that this sheet is under the top sheet. So let's go ahead and take a look at this particular. So this here again is power system.schematic doc, which is this file right here. So you can see already the advantage of this immediately in viewing this. Right here, we have an LM2595 DC to DC converter. Currently, some of you are currently using this already as part of your design. So it makes it simplistic to do this. So I'm going to pause sharing right here real quick. All right, so we are back. 1, 2, 3. So some of you already have had an LM2595 as your DC to DC converter. So this is pretty much the exact circuit you would be using for a 5-volt DC to DC converter. It's good for about an amp. It uses a simple part. It's one chip solution. We have a power port. This is right here. This comes off of this wiring panel, and you get all of these because when you get Altium, some of these panels are not active. So one of the first things you want to do is right click anywhere up here in the menu bar area, and you're going to get this different list of menus you can choose from. So let's turn off pretty much everything. So this is kind of almost like default. First time you ever used it, you're going to want schematic standard, utilities, wiring, maybe formatting, just depending on what you're doing. I don't need formatting. So, and of course you can move all these around however you want. So we'll use that. Now over here, this is the wiring panel. Again, this can go anywhere. I just usually put it on the right-hand side. It's just convenient for me. I can put it right here on this side. Pretty much anything can drag and drop anywhere. So the nice thing about this, I've got wire. Do wires like that, connect things, everything you're probably used to already would do in a schematic. There are ground ports like this. There are power ports that look like this, in this case bar. Now, both of these are actually identical because I can select and make this earth ground again, or I can make it a power ground and rotate it and hit space bar. You can probably hear it in the background. I hit the space bar, rotates the part. And so I can make this ground. So it's just, this is kind of a shortcut. These two are identical. Now I use basically the power port looking one with the little bar. And I label my parts, 5V0 for 5.0 volts. It doesn't matter what you call it. I could call this VCC, whatever the name is, that's going to be the name of the net. So it doesn't matter. I used to years ago actually would put in the exact voltage. Like if I was doing 3.3 volts, I used to do this on a lot of designs. Nothing wrong with that. I just over the years have just adapted this as my format, where I label my voltage as 24V0 with the V being the replacement for the decimal point. That's just what I do. I also have gotten into a habit of color coding my wires, so to speak. So this is kind of just a wire, but you can go in here and change the size of the wire to be something else. You can change it to be a medium size, and you can change the color to anything you want. So I just saw some example projects many years ago, about 15 years ago, where this was done, and I really like that style. And it kind of helps me identify those are power, that's ground, that's 5 volts, 24 volts. I just kind of use different color codes. It kind of varies a little bit from project to project, but I use general color codes to represent the different voltages. So when I look at a printed page, as I print everything in color, it shows up really well. It just helps me diagnose and debug a board quickly because I can look at this immediately and go, I've just got power, I just got random power unknown coming in here on this power port, goes through a fuse, is nominally going to be 24 volts. That's what the client has requested. So that's why it says 24V0. Again, this is technically 8 to 30 volts. All of this is ground, all the green. So it's all connected together. There's this diode, switch out's connected here, but all of this over here is all 5 volts. Hence why it's 5V0. So all that is on one sheet. Another thing kind of to note is I have a title block down here. I do a title block on all projects. You are not required to do that in this class. I'm not going to hold it against you if you do or don't. It is just a good practice to start using a title block. Why? Because eventually you're going to get hired by a company that more than likely has a documentation standard, and they're going to want a title block. They're going to have document numbers to traceability, revision numbers, so on and so forth. So that's all here. In this case, who did the design, the document number so we can trace it in the future, and the revision number. This is revision 1. Sometimes I do revision 1, sometimes it's revision A. Just depends on the customer and how they want to track things. So that is the DC to DC converter, and that's all there is to it from connecting a hierarchical pin. It's just literally come over here, you place this port, and you can give it whatever name and size. I use kind of this like a 300 thousandths size port or 300 pixel wide or whatever it is, and then you can just give it whatever name, my port, and then you specify what kind of I/O it is, an input, output, bidirectional. Bidirectional, so it changes the harness type, the way it looks, and then you just connect the wire to it, and wham, now you've got a port connected. Now notice that it has got these red squiggles. The reason why that's there is because Altium kind of compiles the document as it goes, and in this case, I've got a port here, but there is no my port listed here. So if I synchronize this port symbol again, or the sheet symbol, notice my port comes up. I can add that now to the schematic sheet. And now if I come back over here to the power system, the squiggle is gone. It's basically saying the sheet is compiled correctly. So it's kind of tracking your inputs, outputs, and things like that. So obviously I don't need that here. So I'm going to go ahead and get rid of it. Notice the squiggle now appears here because I'm saying that there's a port pin or a port to this sheet that doesn't exist. So we just come and hit delete. I hope this makes sense to you. All right, so that is one of the first sheets. So now let's come over here to the thermocouple interface. So thermocouple takes in, literally, thermocouple, the direct sensor 2 wires, the aluminum and chromium wires that come from the sensor. We kind of showed that in the previous video on this project. So we bring that in, and then we connect through a chip that we're going to show in a second, but it comes out and connects to our microcontroller using an interface known as SPI, Serial Peripheral Interface. So it uses master in, slave out. In other words, there's a digital out pin where the digital data is going to go from the thermocouple reader into the microcontroller. The microcontroller is going to send clock signals to clock the data out, and there is a slave select or a chip select to actually select and get the data from the chip in question. because you can have multiple readers. In this case, we have one. SPI also has what we call master out slave in. In other words, that's data from the microcontroller to the device in question. In this case, this device does not require that. So let's go ahead and take a look at the sheet. So we have basically these 5 signals. So let's go over here to sensor interface. Can't seem to talk today. So there's our thermocouple inputs. We've got a capacitor to reduce some noise. We've got 5 volts here coming into power, and we have our 3 data lines that we use to control it. So if we take a look at the data sheet for this, which for me, I can come over here and do this data sheet document, because I have the data sheets are actually part of my parameters. Data sheet document, I actually have that assigned as a parameter for these parts. If you probably pull from Altium directly, I don't know if they do that. I pretty much have every data sheet of every part I use is actually stored on my system. So we'll go ahead and take a look at the data sheet on this. And so we've got a maximum 6675. It takes power in here. They're recommending at least a 0.1 microfarad capacitor for power bypass. I'm using a 0.1 and a 10 microfarad for power bypass. So we'll have a little bulk capacitance, as it's known as. They don't show this. I included that. That's just a knowledge after using this thing for a while, just to reduce a little bit of the noise. And then we have master in, S clock, and the slave select. So one thing that needs to be shown here is this signal actually is connected here. So that's something that needs to be done actually on this project. I had left off the ground. So I'm actually using this as an opportunity to correct this board. So let's go ahead and fix this. Is after building this, I'm like, oh, wait a minute, that signal T minus was actually supposed to be ground. So we're going to go ahead and fix that right now and do this live. And so I did. And what I did here, I just selected Control C, Control V. I use copy and paste a lot. So I'm sorry that seemed a little fast. I'll do it again just so that it kind of becomes obvious. So what we needed to do here is I needed to change pin 2 to ground. So this really now is becoming ground. So I'm just going here and deleting all of this, copying this, copying it again, changing the width of the thing, just kind of editing the trace or the wire, and copying the ground signal. So now that is actually the correct circuit for this. So in real life, when I got the prototype for this and discovered that, all I had to do was just short the wire. So blue wires and hacking a board is common. So by the way, don't be afraid if you get your board in and it doesn't work right away. You don't need to respin the board immediately. You need to get the board working. You make corrections to the board, cutting traces with an X-Acto knife, blue wire, etc. Perfectly normal. In fact, did that on this design. So this is all there is to the thermocouple system. So this entire sensor comes in, gets read by this chip, and it talks digitally. So this chip does all of the work for us. It is a cold junction compensating, meaning it's reading the temperature of this. If you study thermocouples, you'll know what this means. And it's a thermocouple to digital converter, aka analog to digital converter, because this is an analog signal. It has some analog front end conditioning because it's a really, really tiny voltage that's being sensed as a thermocouple to basically temperature on by different types of metal, by different types of contact metals, in this case aluminum and basic chromium, coming together creates a voltage just by their contact. And the voltage is related to the temperature at which they're exposed to at the junction. So you have to know that, and of course the junction temperature at which they come to the device to be read is incredibly important to know. And then there's a very non-linear function that converts this to Celsius. So that's all being done internally to this chip. So we get Celsius as an output. It's 12-bit resolution. There's all sorts of programming information. How the data comes in is the SPI interface. The chip select here, we clock the data out, and there's 16 bits of data that we read. So we do all this. In fact, this data will even tell us whether or not the the device has been, the thermocouple's been disconnected. It's an excellent chip for this, by the way. So if you're actually using any thermocouples in your future projects, this is the chip to use. It's actually not a very expensive chip either. So we have that. It's a simple one-page schematic, and we're done with this page. Coming back over here, so you know now this T minus doesn't exist anymore, so I'm going to go ahead and delete that. And now we're going to copy this and connect it to ground. So now we're completely done there. So that page has been updated. All right, so moving on here, we have a relay. We'll cover the microcontroller now. So we have the relay. Relay is just simply basically a remote controlled switch. Think of it. It's controlled by a solenoid coil. And so this is supposed to be a 10 amp relay that's going to switch whatever voltage that the client wants up to 240 volts AC through the switch. So we have a normally closed and a common contact. So with no power at all, this board is unpowered and there's no power going through the relay, this is shorted to this contact. These two pins are shorted together. When this relay is engaged, in other words, there is current going through the coil, then this contacts, the common is shorted to the normally open contact. So let's take a look at that page. I call that power control. I have two metal oxide varistors. These are due to reduce voltage, basically spikes, sparking, for lack of a phrase, from when you disengage motor contacts and things like that. So if this was driving a motor or anything that was pulling a lot of current, when you reduce that current, it wants to keep it so it'll spark. That is not a good thing for electronics. So you put some MOVs out here to kind of absorb that spike, basically. So we have our common and our normally closed and normally open contacts. So here's the symbol, just like we were talking the other day about the symbol of a relay. So we've got the normally, or the contact, and then the normally closed, normally open is drawn, so it's obvious which one is which. This clearly is unpowered. This is the normally closed, and then when it's powered, this plunger will push in because of the magnetic field, and the normally open contact will be shorted. So we have the live or power section. This is the power we're controlling. It is completely isolated from the rest of the circuit. There is no electrical connection between this side of the circuit and this side of the circuit. This is a magnetic field is the only interface in a plunger. Over here, we've got a 5 volts coming in onto a transistor, and this transistor is being driven from the microcontroller directly. We push current into, or basically current is being pulled. So this is 0, this transistor activates, current flows, goes through the relay, and the relay turns on. If there's a high signal on this pin, then, or it's just open, no current flows, the transistor is off, the relay is off. These two I've covered before in other lectures. This is for preventing spikes from reoccurring on your main power lines. So we've got an inductor basically here. It's a coil of wire. And when that coil is energized, it has a magnetic field. When it's de-energized, that magnetic field wants to still be present. And so being an inductor, it basically tries to keep the current flowing in the exact same direction, which means it builds back EMF or reverse voltage. So instead of 5 volts, positive, negative here, it'll be minus 5 volts immediately with an instantaneous moment. That's not good for your power supplies to see that. So just to kind of prevent that, it's just a good preventive measure. You put a capacitor and a diode in a reverse direction here, and that will suppress that spike immediately. So that is the relay control circuit. So now that leaves us the microcontroller mainly. So we've got connected to the microcontroller, we've got 4 user switches. So we got 4 pull-ups connected to 5 volts DC. Pull-up, by the way, will basically work because there's no current flowing into the microcontroller. The microcontroller is just monitoring the voltages. So 0 amps are coming in. If there's 0 amps going through resistor, the voltage drop across said resistor is 0 volts. So the voltage here at this node is 5 volts if the switch is not pressed. If the switch is pressed and there's now current flow through the ground to ground here, the voltage at this terminal obviously will be ground. So basically we're making a 1 or a 0. Many years ago, you would have to do a circuit called a switch debounce because actually when you press momentary switches or any switch, there is mechanically what is known as bounce, where actually it will make contact, no contact, contact very quickly in microseconds time. And that can actually, if you have a state machine driving, it can sometimes get confused because of the bouncing of the switch. With microcontrollers, you can get around this by writing an algorithm that's called a switch debounce algorithm that basically replaces the circuit that you used to have to do for this. And that circuit was basically just effectively a filter or some filter and sometimes a flip-flop. So we basically get rid of that with just simply reading it and then verifying that the switch actually did change state and then pausing for a few microseconds. So that's our switches, and we're going to read that on port B here. So let's go ahead and take a look. So we got a microcontroller. We have we kind of covered this in the symbolic symbol because this is the exact same microcontroller we built the symbol for. So we have port A, port B, port C, some SPI ports, and we're also using port B down here for I2C purposes to talk to a display. So let's go ahead and take a look at the microcontroller schematic. So right here is the PIC16F73. This is the very symbol that we made the other day. We have port A, port B, and port C. So you can see why I did what I did in creating the symbol and broke everything into basically port groups. This here is the crystal that I was talking about for oscillating the clock oscillator on the actual microcontroller. It's conveniently, like I said, conveniently the width of the pins was set such that the crystal symbol would fit exactly between the pins. And that was done so that I can actually draw my schematic like this and everything will be nice and neat and pretty. I mean, if you wanted to, you could, if you had two pins side by side, you would have to end up doing something like if it was these two pins, you would have to end up doing something like this. And, you know, it works, but it's not as visually pleasing, so to speak. It's not as easy to read. So I prefer doing it like this. I've got my power and ground over here. So pin 20 is 5 volts. VSS is pins 8 and 19, and they're connected to ground. This here is the programming interface. So there's actually a device that I hook up to my laptop that I do, or desktop, depending. That I use MP Lab, which is right here. This is MP Lab. So if I press this button right here, and I had the board connected through an ICD4 for microchip, or a PIC kit or PIC start, or that's a PIC kit 3 or a PIC kit 4 programmer, and it connects through this connector, and all it needs is power and ground, master clear, clock, and data. These specific pins. If I do that, it will program the contents of this, the flash of this processor directly. So that is how code is loaded into this processor, is through this port. And then down here, we've got a little communications chip. So this client wanted UART communications for future proofing. Currently isn't being used by any purpose, but we added this communication for eventual firmware that would use this. And so we talk over what's known as an UART, an asynchronous, universal asynchronous receiver transmitter. And that's what UART stands for. I've talked about it, I think, in the previous lectures on, I think, on microcontrollers. These talk at TTL levels, or 5 plus, basically 5 volts, that are transistor logic. But that is not how RS-232. RS-232 is an electrical standard for UARTs, and RS-232 is plus or minus 12 volts. So the actual wire is this signal here, a 1 and a 0 is either plus 12 or minus 12. So what this device does, this is a chip from Texas Instruments, it actually produces the proper voltages, but instead of having to have a plus or minus 12 volt power supply, because you don't see plus or minus 12 volt here, it uses what's known as a switched capacitor DC to DC converter. It takes these 4 capacitors and internally builds the plus or minus 12 volts that it needs to do RS-232. Maxim Semiconductor was one of the first manufacturers to build this, and is very common. These chips are pretty much everywhere today for serial port purposes. So you no longer have to have plus or minus 12 volts as a separate power supply. You just use one of these chips and 4 capacitors. So it's really nice. In fact, this chip is what, well, it's out of stock, this one here currently. So, alrighty, so that's pretty much the grand tour of the schematic for this board. Last thing was going to the other board. There is two boards to this project. There was a display. So again, this board had an LED display, 7-segment display. So we wanted that to be at a 90 degrees angle, and I'll be showing how this interfaces to each other as a complete product here in a moment. So let's go ahead and take a look at the display schematic. So that is here. It's a simple one-page schematic project. So that's this project here. And we have a 7-segment display. And just so that you know, 7-segment displays actually are basically you're driving one segment at a time, one digit, and you're having to scan it. So the microcontroller is constantly driving this display to keep the LEDs on long enough that visually it looks like the numbers are always on. In reality, digit 1's on, and then digit 2 is on, and then digit 3 and digit 4, and then it recycles. So whenever a digit is not on, it is actually all off. So you control which digits on with these cathodes here. So these are all LEDs. There are 1, 2, 3, 4, 5, 6, 7, 8 LEDs that are being driven for each individual digit. And each LED is like one part of each segment. And of course, the decimal point for each one. When I turn on the cathode, so if I wanted to light up all the same value, if I wanted this to say 8888, I would light all the segments. If I wanted 8 and all the decimal points, I would put all these as highs. I'd put, basically 5 volts on all of these, and then turn on all these cathodes, and then the entire thing would light up. But obviously, if I want 0001, I would have to light up all the different ones, and then set each digit, and then set only the first two to be right hand side here of these digits. So obviously, you've got to write an algorithm in code to do this, to basically turn an ASCII character into a 7-segment display character and turn on the LEDs. To do this, I used what's called a port expander, because this requires 16 with that, and plus these 4 LEDs for enunciators on the side of the board, which I'll show in a second. I needed 16 I/O lines. Well, I could have used a massive connector and a microcontroller that had more I/O lines, or simply use a port expander. This takes in I squared C over this basically connector. All I squared C is a 2-wire digital communication bus, chip-to-chip communications, and he has a clock which is coming from the master, or in this case the main microcontroller, and the slave, which is this chip here, and it just receives the data and does what it's supposed to do, which in this case is provide 2 8-bit I/O lines, and each one of these I/O lines can be either input or output. I've got them configured in code to all output, and it drives this entire board. So I send serial data over these 2 wires, and I can control all of these LEDs. So that's what's happening here. So we have some power decoupling here, just to provide a little local power. And then we have our resistor limiting current. So basically here we got 5 volts coming into this LED here. This LED, let me pull up the data sheet on it, has for a red LED is 2.2 volts forward voltage. So if I want to have approximately 10 milliamps-ish running through here, then I have 5 volts minus roughly 2 volts. It gives 3 volts divided by 300 gives me 10 milliamps. So basically, you just do a little mathematics using Ohm's law here and nodal voltage analysis, because the node voltage here is going to be the forward voltage drop when this transistor is turned on. When the transistor is turned off, there's no current flowing, so it doesn't matter. So transistor's on, this terminal's at ground, which means this terminal here, this node's at roughly 2 volts, and then I can compute the current using, so basically I compute what resistor I need here. That determines, and the more current you have, the brighter the LED, the less current you have, the dimmer the LED. So pretty straightforward. So that's basically what we have here. Not a whole lot to it. So let's go ahead and now take a look at the the circuit board for this. So now we've got everything. Notice here, all these parts have a corresponding footprint. Resistor, LEDs, capacitors here, the 7-segment display, the transistors, everything has a footprint. Even these little mechanical standoffs here. Oh well, they This is a bill of material item, but you'll see this. You'll see the standoff in the 3D view. So everything on here has a footprint. So it has a symbol and a footprint. So now let's go ahead and take a look at the corresponding board layout. So this is the board layout. Flip it back over. So might look a little confusing because there's parts on both sides of the board. So let me put it in 3D view so you can see the board. So physically, this is what the board would look like, and in fact did look like, and this has been in production already. So we have 7-segment display here. We got 4 LEDs in the corner. So this is going to be on the side that is facing the user out of basically a view window, a transparent piece of plexiglass. A little view lens is going to be over this. And the user is going to see 4 LEDs from the corners, and then of course see the temperature being displayed here on the 7-segment display. So I don't want any other parts on here because this is on one side. So all the parts went on the bottom side of the board, including these 2 standoffs I was talking about earlier. So here's the connector, here's the port expander, and here's all the transistors we looked at a moment ago. So let's go ahead and take a look at this layout. Go put it back in TD. So if you use Altium, you switch back and forth with the number 2 and number 3 key, 2 for 2D view, 3 for 3D view, 2, 3, 2, 3. Pretty basic. And when you're in 3D view, you kind of get used to using basically the control and the shift key here. So the control lets you zoom in and out by moving the mouse, and then the shift key, you can, without hitting shift, you can drag around, and shift and moving around helps you rotate. You can also use a 3D mouse, which I also have. All right, so let's take a look at the top side of the board. I'm going to go into this. This is a 4-layer board. So that is designed here with our layer stack manager that can define the number of layers. Normally, you're going to be doing a 2-layer board probably for this class, but I have quite a few students that do 4-layer and even 6-layer boards depending on the routing. To add layers, you just come here and just go insert layer above or layer below, and it can be a signal or a plane or core and prepreg if you're adding in the insulation layers, which there always has to be an insulation layer between it. You don't need to get into too worry about the details of this. I mean, I can explain more about the different layers, dielectric strength for doing controlled impedance boards. That's where that really becomes critical. For the boards we do in this class, everything the manufacturer is defining the board stack up for you. So you don't have to worry about what core to use and what prepreg to use and what is the dielectric strength of the material or dielectric constant of the material. You don't have to worry about any of that for anything you design in this class. In the future, you might have to, but for everything we do here, you don't. So again, this is a 4-layer board. I do that because I wanted the power and ground to be inside. I didn't have to worry about routing the 5 volts and the ground. So here, top side of the board, I hit Shift S. That is the hotkey for the Shift, and S goes into single layer mode. And you can see all of the traces that are on the top side of the board, which is not much. In fact, the only traces that are on board is basically the LED interfaces. And that's again because really everything happens on the back side of the board. Everything on the top side is really just reserved for the display and the LEDs to indicate. Let's take a look at the overlay. Overlay again is the text that's being displayed on the board, the paint to indicate the where the parts go. So this is LED 4, LED 1, 2, and 3, and LED 5, where the display is. So let's take a look at the back side of the board. So obviously, as you can see here back in a normal view, everything is backwards because that's the back side of the board. So when you flip the board over, it literally flips the other way and reads correctly, but we're looking from the top side down. So to do that, you hit Control F, and that flips the board. And of course, now if you notice, the top side is backwards and the front side or the back side now reads correctly. And so let's look at the bottom overlay. There's Shift S and that, so you can see all the text looks correctly. And it kind of gives you an indicator where the parts are. These are capacitors and these transistors here. There's the connector that's going to go between the boards, so on and so forth. Here we have this chip, this port expander, and I've got everything laid out here. And you notice as I highlight a net, it highlights the entire trace and the full net, like ground. If you noticed, all the ground devices are all outlined. So let me show you this thing at the advantage of a 4-layer board. So we have ground here. This pin here is connected to ground. And so we have this trace and this via. So this pin needs to go to ground. This is known as a via. This is a barrel through the board. It's drilled all the way through, has what's known as an annular ring. That's the blue part here. Of course, on the top side, it's going to be red. So that's copper. That's there. And then in this case, this is a 30 mil pad, and this can be different sizes. I can make this 90, it doesn't matter. Of course, it shorts everything out. I do that. So it's a 30 mil pad for the circle, but the hole is a 15 mil hole. So there's a drill, it drills the hole, and then they plate the barrel of the hole. And so it actually has copper down the entire side. So the advantage of that is that goes through the board, and any inner layer can connect to the via. Sometimes you don't want that because anything that's not ground, you don't want connected to that, like lead 5-7 net here. We don't want ground connected to that. So if we look at the ground layer, all that you see here that's not green, this is all copper. So it's kind of it's a negative image. So if you notice, there's no green here. So basically, this via is actually directly connected to the copper. There's different connection styles, but I use direct connect for this to get maximum copper connection. And if you notice, like here on these signals here for these LEDs, which go through the board, they are completely isolated. So the ground layer will not connect to that. Now, so that's ground. You notice all the grounds look like that. If we go to power, which is in our case 5 volts, the 5-volt layer does that for its vias. And of course, everything else is isolated. So when they build the stack of this board, they will have 4 separate sheets of copper, basically, and then they kind of glue it together, mate it, and drill it, and it's all put together. So the process is fairly sophisticated to build a circuit board. Now, the bottom layer, we are actually doing all our signal routing on the bottom layer. So what I did here to make it convenient, notice everything just happened to flow just perfectly from, left to right here. Everything was symmetric, it seems. Well, that wasn't by accident. That was done by choice. Because what I did is I positioned everything, and then I just moved the nets around, what basically port 0, digit 2, digit 3, etc. I figured out what the optimal configuration was and just connected the appropriate digit or LED to the appropriate port pin to make it do that. That was not, like I said again, that was not by accident, it was by choice. So initially, I think I had it A, B, C, D, E, F, G, decimal point, digit 1, 2, 3, 4, lead A, B, C, D. It was the very first rendition. I knew doing that would not end up like that. So for the person writing the firmware, which in this case was me, I don't care if port 00 is B and lead C is on 07 or vice versa. It doesn't matter. This is just a number to me in the compiler. I just assign this. In fact, to kind of give you a glance of that, that's assigned over here in a header file where I assign all these different port pins and all of these configurations are all assigned different values. So it really makes controlling this much simpler by basically doing it that way. In fact, here I've got it all set up here. Digit 4 on. I use these macros here to control it. This is so in the code, I just do digit 4 and on and off, or lead E on or off to do that. So I figure all that mapping is all done up here. Once it's done, it's done. So from electronics perspective, I can move these around however I want, which makes routing a whole lot easier. So now everything is connected. And just to kind of show you how routing does, and I have a separate video I'm going to be posting later on routing something so you can see some routing techniques. But so here we're just going to take and use this. This is now PCB standard and wiring, and on your menu selections. And this is the interactive route connections, or control W. I always just click this button. And so basically you get this little reticle. You just go to the net you're interested in. The system just sort of snaps to it. And so you can see here, this pin wants to go here, and there's a white line here. So I can just draw, and I can draw it however I want. And I can hit tab and I can change the width. You notice over here, the width is there, and I can make this 80. Of course, if I use 80, it doesn't want to go anywhere. It's too big. I could use 10, and it's a little bit bigger. I could use 20, and it's even bigger. So let's go back to 8, and we can place it up here. And of course, notice it won't let me route anywhere that, it tries. It's hugging and moving around because it's not going to let me intentionally short the trace. So let's go ahead and route it up like this. And I'm going to just show this, and I'm going to go back to the way it was in a second. So that is a hand routed connection. Basically, that was manually routed by me. I did not use an auto router for that. So just put it back the way it was. So notice the nets have got all their labels, so we know exactly what it is. This is net A, digit 4, E, D, decimal point, so on and so forth. So that is kind of the general routing concept. So this was all done by hand. I placed all the components in order, neatly, took my time, made sure everything, computed everything. Alex said I have a routing video I will be posting where I go over that in a little bit more detail. So that's basically what's happening there. So let's just save all this. Now let's go over, and so let's again look at the 3D view of this board. So we have this, right? So that's our display. Now let's go over to this board. So this here is the actual controller board. So this fits into a case. It's 2.420 inches by 3.75 inches. Kind of same thing. Got some information on it. Here's the connector for the display. I'll be showing that in a second. Here's those 4 switches. Here's the microcontroller. Pin 20 was power. I kind of remember that from earlier. There's power. There's the decoupling capacitors to provide a little bucket of charge. There's the crystal oscillator we were looking at earlier. So and so on and so forth. And the way when you route things, you kind of group all the parts together. So for instance, we were looking earlier at the relay. The relay had 2 MOVs, the relay itself, this capacitor, diode, and transistor, etc. Well, when I did it, I actually found all those parts and kind of grouped them together. And you can sit here and rotate the part around using the space bar here. You can rotate around and get everything lined up where you have really short traces between everything. Again, also used power and ground layers for everything. So anything that was pulled up from the power plane was direct connections for 5 volts, and ground, anything that was ground was directly connected. Notice though, I've got for this big AC area, I've basically created an island where over here in this corner of the board, there is no copper except for the connections themselves to the terminal block. That is done because I don't want any possibility that AC would get onto the ground or power lines. So we just isolated it with a big, what we call basically it's a, let's see, solid region as it's called, or a fill. So this here actually connects, this is again single layer mode, this connects this terminal block to the relay and the MOV. Same thing happening here. These traces are both on the top and bottom side to carry the current. I use the trace width calculator that I've mentioned before in class to calculate the appropriate size of the trace to carry the 10 amps through the relay. This here is the actual part itself. So common is over here, and there's your 2 switch contacts, and these 2 contact points here are the actual coil that we're engaging. So you put current through here, and it turns on and off the relay. This here is the 5-volt power supply, the LM2595, the fuse. Here's the main connector we looked at earlier. This is our input from the thermocouple system, which I'll update later. To do that, you can do design import changes. By the way, just if you're coming from your design, like we made some changes here earlier where we got rid of T minus and made it ground, I literally come over here and go tools, or excuse me, design, import changes from DBI relay control. It tells you everything that's going to do. It's going to remove this net, do this, do that, and the other. You're going to click execute. It does all the changes. You close, and actually now you'll notice that this pin is now ground. So that is completed. So now that we've got that done, I have to change this. I also changed DC to DC converter stuff, so I technically need to reroute this a little bit. So effectively, what we have is this board here has this communications device here, the RS-232 that we're talking about. Um, it has this basically inductor and diode here. These two actually connect. This connects over here. So we'll just do it like this. And then technically, so that I can kind of connect the 24 volts here, I'm going to just put a via in and come over here to the bottom side and just connect a 24 volts up to it. So what you do, notice what I do here is I do copy and paste. I have a via style I like, via size I like, and I just copy and paste. You can put it anywhere on trace. Now there's a via, come over here and just, and see a nice thing here, it automatically knows I want to do interactive route connection. So I just click it and boom, connected. So now that made that modification. Just so you know, what you didn't see is I had changed this part earlier in the day to a different version of this part, LM2595. It was a 25, I think 96. And so the pins are a little different. And it's because of stock reasons. The 2595 is actually an ideal part. And so that's why I made this change. So probably want to clean this up just a little bit, just to be a little nicer. Yeah, we'll do that. Voila. So we have our power supply, we have our inductor, we have our two caps. I said earlier, we have crystal, so on and so forth. So it's pretty basic routing. In fact, everything on the bottom side of the board is very minimal. Top side of the board, again, minimal. Basically, most of the connections are over here to these switches and over to the ICD connector here for programming. Couple signals here going up here for the communications. And then the 3 signals going over to the SPI port that we have. Serial peripheral interfaces going over to the thermocouple connector or reader converter. So that's pretty much it. Now, if you notice, I also have this overlay. I have this fabrication notes, as it's known. You don't need to do this. I include this. It's a good idea to have a version of this so that people read it so they know what you're building. This is basically board configuration and board statistics. I've been using this very same template for literally 14, 15 years. A lot of times you don't need to include this to get your board made at all. So it's pretty straightforward. So one of the big things though is also this boundary layer. So we have all these different layers. This is a 4-layer board, but I have one layer, it's a mechanical layer known as the boundary. And the only thing on that layer is the boundary. It's these 4 traces. The traces define the board. So what you do to define the board shape, which is in this case is the black outline of the board where you can actually put your parts, is you highlight your boundary traces, come up here to tools, design, board shape, define board shape from selected objects. Once you do that, it changes it. So like for instance, I can take this, if I wanted this board to be much wider, I can do this, or make it this size. So I just drag in the middle. And I wanted to make it literally the board look like this, with this little point, I could do that. Just come here, board shape, define from selected sizes, or from selected objects. You can do that. I can come in here, make the board wider, select the traces for that. Board shape defined from selected objects, boom, do that, so on and so forth. Surprisingly, you can do things like circles, weird shape. I mean, you do all sorts of weird shapes. I did a sensor the other day, a little tiny circuit board that's not much bigger than a dime. And it was for a temperature sensor controller. And literally the circle, if you will, is nothing but the outline of this was a circle. I did another project for a reticle for firearms, basically reticles for pistols, and it was a weird shape for a battery holder, and did the exact same. The weird shape, and all you have to do is the mechanical layer. Problem solved. It's fairly straightforward to do. So that's how you do shapes. Of course, most shapes you're going to do in this class is going to be probably rectangular, perfectly fine. In fact, I think probably a lot of the prototype companies pretty prefer that you not have odd shapes for your boards. But if you use PCB Way and PCB Way and JLC PCB, I think they'll let you do odd shapes. So that's pretty much it. Let me now take a look at the 3D view of this board. So what I have done, I've exported the step file out of the other board, which by the way, to do that, you just come up here to File, Export, Step 3D, and it'll export the step file. And you can go ahead and do that and just export all. And it'll generate and tell you when it's finished. And then all you have to do is end up basically adding design, add in a 3D body, and you can then select the 3D body and import it in. So fairly simplistic process for bringing all this in. So in this case, I brought in the 3D body. That is the board that we're mating to. So you notice there's the connector and the mating connector. So so I can verify that when it's screwed on correctly with the right angle standoffs and the proper standoffs being here and the screws, everything mounts correctly. So you can completely see how all this will interface. That took a little time to get that perfectly right. Here's their connectors on this side. So this is where, like the electrician would put in wires and you push in on this little spring-loaded contact and the wire would push in, it's stripped, and you can end up unplugging and plugging in the connector. Same thing with this one here. You take a little screwdriver and you're able to unscrew and screw in the larger wire for the AC contacts. So there's the relay, there's the inductor, there's the microcontroller, so on and so forth. And then I also included the step file of the actual enclosure that we're using so we can actually see what the system would look like. I've got it set to kind of partial opacity because, I wanted to see the electronics in it, but technically I can make it 100% and it looks like this. But of course, you really can't see what's going on when you do that. Kind of defeats the purpose of the electronics design. So I usually kind of leave this as a low number so I can see what's inside the box, so to speak. But the actual device, when it was made, looked exactly like this. In fact, when we built the prototype and put everything together, other than tweaking a little bit of had to remove a little bit of circuit board material here because it was just like literally the dimensions for the box versus what was in the data sheet was off by like 2 millimeters, if that. It just made it, and so we just had to shave the board a little bit to slide it into the box. Other than that, it fit like a glove. So. Well, that pretty much sums everything up here. I'm sure you probably have some questions, so please email me or call me at some point if you need to discuss. But this is the general process for circuit board designs from beginning to end. Basically in a nutshell. I will have some other videos where I go over a little more detail of the process of the routing. So definitely look for those. But other than that, that should complete us. All right. So have a good one. Bye.